This video provides an introduction to the one-sample t-test, which tests a hypothesis about a population mean. We collect data from one sample and calculate a sample mean x-bar. We then compare this mean to the distribution of all the possible values we could have gotten, assuming that the null hypothesis is true. This distribution is called the sampling distribution of the mean. Let's review what this distribution looks like. We know that its mean, mu x-bar, is equal to the population mean, mu, and that its standard deviation is equal to the population standard deviation, sigma, divided by the square root of our sample size, n. The standard deviation of a sampling distribution is called the standard error. We also know that if a population of scores is normally distributed, then the sampling distribution of the mean will also be normal, no matter how small our sample size. Finally, the central limit theorem tells us that if our sample size is large enough, 30 or more, then the sampling distribution of the mean will be normal, no matter what the shape of the population distribution. All of this is important because it allows us to develop the model that represents the null hypothesis. This is what the model looks like when standardized, that is, as z-scores. We can standardize our sample mean x-bar by subtracting mu x-bar and dividing by the standard error, except for one little problem. We don't know what the population standard deviation is, so we can't determine the standard error. So now what? We substitute our sample standard deviation for our unknown population standard deviation and carry on. Now, instead of the population standard deviation sigma in the numerator of the standard error equation, we have the sample standard deviation s, or SD. Sigma is a constant. Our sample standard deviation is a variable, which we use as an estimate or best guess of sigma. Sigma over the square root of n in the z-test formula becomes s over the square root of n in a t-test formula. Sigma is a constant, so we have introduced variability into the equation by substituting the sample standard deviation, which is a variable. The t-test accounts for this variability. Note that the only difference between these two formulas is that we have the actual value of the standard error for the z-test, but must estimate it using our sample standard deviation for the t-test. T-distributions look like the normal distribution, bell-shaped and symmetric, but rather than one distribution, they are a family of distributions. Here is the normal distribution in black and several members of the t-distribution family. T-distributions are sample size dependent. Their shape depends on how large our sample size is. Determining the specific distribution requires a calculation called degrees of freedom, abbreviated DF. For a one-sample t-test, the degrees of freedom is the sample size n minus 1. Here, the normal distribution is depicted by the solid line, and different t-distributions are shown by various dashed lines. Note that there is more area in the tails and less in the center of t-distributions than in the normal distribution. Also, as sample size increases, the t-distribution comes closer to normal form. Here is another example of the normal distribution and several t-distributions. The distribution in the upper left is the normal distribution. If we set our significance level at 0.05 for a two-tailed test, we know that the critical values of the test statistic are z plus or minus 1.96. For a t-distribution with 2 degrees of freedom, these values are t plus or minus 4.30. As you can see, as the sample size increases, the critical values of the t-distribution come closer to that of the normal distribution. With one-sample t-tests, we generally compare our results to some known standard, such as previous research results. For example, we might know from previous research that the resting heart rate of healthy adult males is 80 beats per minute. So in our research on elite male athletes, We might want to compare their resting heart rate to this standard to see if it's different. There are three assumptions for the one-sample t-test. The first is random sampling, which in reality means that the sample is fair, or unbiased. We want to be able to generalize from our sample to the population of interest, so it's important that the sample be representative of that population. What type of elite athletes are we interested in generalizing to? Results for sumo wrestlers, for example, might be very different than for professional soccer players, so we would need to specify our population in order to select an appropriate sample. The second assumption is independent observations. One athlete's heart rate should be unrelated to another's. This means, for example, that we do not have repeated measures for any of the athletes. The final assumption is that the underlying population distribution is normal. The central limit theorem tells us that if our sample is large enough, 30 or more, our sampling distribution of the mean will also be normal. The next video presents an example of the one-sample t-test.